Every time you hear that sickening thud, that bone-jarring impact that makes your teeth rattle and your heart sink, you aren't just hitting a hole in the ground. You are witnessing the final catastrophic stage of a microscopic war being waged beneath your tires. Potholes aren't just bad luck or old age. They are the result of a precise, scientific failure of engineering involving fluid dynamics, thermal expansion, and structural fatigue. In the United States alone, road damage costs motorists nearly $3 billion annually. But why, despite all our modern technology, does the ground literally open up and swallow our commutes? Today, we're going behind the curtain of civil engineering. We're exploring why asphalt fails, the hidden role of asphalt voids, the lethal impact of water, and the high-tech tools, from depth gauges to Benkelman beams, that engineers use to fight back. Before we can understand the failure, we have to understand the material. Many people call it blacktop, but in the industry, we call it HMA, hot mix asphalt, or asphalt concrete. It's a composite material. Think of it like a granola bar. 1, the aggregate, the rocks and sand, the oats. This provides the structural strength. 2, the binder, the liquid bitumen, the honey. This is the black, sticky petroleum product that glues the rocks together. When engineers design a road, they aren't just dumping rocks and glue. They are managing the air void content, the science of voids. If an asphalt mix is too dense, 0 voids, it has no room to expand in the summer heat and will bleed or rut. If it's too porous, too many voids, it becomes a sponge for water. The sweet spot for most pavements is around 4% air voids after compaction. If a contractor fails to hit this metric, the road is doomed before the first car even drives on it. This is where precision matters. To ensure the pavement is laid to the exact thickness required to support heavy loads, engineers use an asphalt depth gauge. Technical note: an asphalt depth gauge allows inspectors to verify that the hot lift of asphalt meets the design specifications. If a road is designed for 4 inches, but only laid at 3.5, the structural capacity is exponentially reduced. Why do roads fail? It usually comes down to 3 primary enemies: water, load, and temperature. Enemy number 1, the water intrusion, permeability. Water is the universal solvent, and it is the primary enemy of asphalt. When water penetrates the surface through interconnected air voids, it begins a process called stripping. This is where the moisture gets between the aggregate and the binder, physically peeling the glue away from the rock. Once the binder strips away, the rocks are no longer held in place. They begin to shift. To measure how leaky a road is, we use tools like the NCAT asphalt permeameter. Specifically, using the NCAT asphalt permeameter, alternate top section allows technicians to test a wider range of flow rates, ensuring the pavement is sealed tight enough to keep water out, but breathable enough to remain flexible. Enemy number 2, the freeze-thaw cycle. This is the pothole engine. Water seeps into the voids. It gets cold. The water turns to ice. As we know from basic physics, V-ice approximately equals 1.09 times Vi water. That 9% expansion exerts massive internal pressure, cracking the asphalt from the inside out. When the ice melts, it leaves a hollow cavity. The next car that drives over that cavity collapses the surface. Boom. Pothole. Enemy number 3, heavy loading and deflection. Every vehicle causes the road to flex slightly. This is called deflection. If the road flexes too much, it develops alligator cracking, small interconnected cracks that look like reptile skin. How do we prevent these failures during the design phase? We use the SuperPave system. SuperPave, superior performing asphalt pavements, was developed to give engineers a way to tailor asphalt mixes to specific climates and traffic loads. A critical part of this process is aging the asphalt in a lab to see how it performs over 10 or 20 years. Using a SuperPave oven for asphalt pavement tests, engineers can simulate short-term aging, what happens during mixing and placement, and long-term aging, what happens after years of UV exposure. By baking the samples, we can see if the binder becomes too brittle. A brittle binder cracks, a flexible binder survives. But testing the mix in a lab isn't enough. We have to test the finished road while it's in service. This brings us to one of the most iconic tools in civil engineering, the Benkelman beam. Measuring the bounce with the Benkelman beam. Named after A.C. Benkelman, this device is a long calibrated lever used to measure the rebound deflection of flexible pavement under a moving wheel load. Here's how it works. 1. The beam is placed between the dual tires of a heavy truck. 2. As the truck moves away, the road springs back up. 3. The Benkelman beam measures that tiny movement, often in millimeters. If the deflection is too high, it tells engineers the subgrade, the dirt under the road, is weak or saturated. It's a literal health checkup for the highway. We've all seen road crews doing throw-and-go patching, dumping cold mix asphalt into a wet hole and patting it down with a shovel. Scientifically, this is almost useless. Why patches fail? 1. Poor bonding. If the hole is wet, the new asphalt won't stick to the old road. 2. Lack of compaction. Without high pressure, the voids in the patch are huge, often 15 to 20%. 3. The bathtub effect. If you don't seal the edges of the patch, water just runs into the seam, gets underneath, and blows the patch out within weeks. The solution: better maintenance technology. Modern solutions involve infrared patching, where the old asphalt is heated up and remelted, creating a seamless thermal bond between the old road and the new material. This eliminates the seam where water usually enters. The science is evolving. We are now seeing 1. Self-healing asphalt, infusing the mix with steel wool fibers that can be heated by an induction machine to close microcracks before they become potholes. 2. Plastic modified bitumen, using recycled ocean plastics to increase the flexibility and lifespan of the binder. 3. Permeable pavement, designing roads that actually want water to flow through them into a managed drainage system below, preventing runoff and hydroplaning. However, no matter how smart the asphalt gets, we will always rely on the fundamental testing equipment. You cannot manage what you do not measure. Whether it's the permeameter checking for water resistance or the Benkelman beam checking structural integrity, these tools are the frontline defense against the crumbling of our infrastructure. Infrastructure is the invisible backbone of civilization. It's easy to take it for granted until you're staring at a $500 repair bill for a blown tire. But understanding the science, the voids, the permeability, the deflection, and the thermal stress is the first step toward building roads that last decades instead of seasons. At Certified MTP, we provide the professional-grade equipment that engineers and contractors need to ensure every road is built to the highest scientific standards. From the lab to the job site, precision is the difference between a smooth ride and a total road failure. If you're interested in the technical side of construction and materials testing, make sure to check out our full range of asphalt testing equipment on our website. Thank you for watching. If you found this deep dive into the science of pavement helpful, please subscribe to the channel and like this video to help us keep bringing you more engineering content.